for this class. Class being recorded.
Professor?
Yes.
Wait, sorry, would you
Yes.
be able to tell us the amount of questions for the midterm or no?
About 12 to 14 questions.
Do they have parts or some of them?
Yeah. Some of them have parts.
Okay, and also the last class, the scheduled class is August 17th, right?
That's right.
And that's the day of the final as well?
Yeah, if we finish on time.
Okay, got it. Thank you.
You're welcome. All right, we'll start with Rhine 3.58. Then Jazelia 4.113, Ivy 4.19, then Yuri 3.511, Israel 4.23. Then we're going to chapter 5 today.
Am I good to go, Professor?
Yes, you're good to go, Ryan.
Okay. So my question was question 8 from section 5. And I know it's an optional topic, but I personally found it interesting. So the question asks us to discuss the solvability of this system near basically 0, 0, 0, 0, 0, -2. Yeah. And it mainly wants to know for the solvability of u, v, w in terms of x, y, z. And so the first thing to notice is that there are 6 variables, but only 3 equations in the system, which basically means that it's not solvable by normal means, or at least it would be very difficult. Which is why it really wants to know, is it solvable? Should we have a specific point that we can reference? And so the first thing to do is to basically get rid of these zeros. So these right here, I basically just kept these functions and just named them f1, f2, and f3. The next thing to do is to set up a matrix of the derivatives of each of these functions in terms of u, v, and w. And of course, these are partial derivatives. So in doing that, I got 1, 2v, and 0 for the first one. So partial derivative of u is just 1. Partial derivative of v squared is 2v, and there is no w to derive. And I basically repeated the process with function 2 and with function 3. I then solved for the discriminant of this matrix, and I got 1 plus 4uv. Now, the next thing to do after that is to plug in basically these coordinates. Basically, we're looking for anything near 0, 0, -2. So that's going to be 1 plus 4 times 0 times 0, and that's 1. And the main thing we were trying to see is the discriminant equal to 0? Because it's not, by the general implicit function theorem, the system is in fact solvable. Is it easy to solve at that point? No. Is it entirely possible? No, but it should. So that's what the discriminant not being equal to 0 means.
Very nice. That's good enough for 3.5. So which is optional So it will not be on the exam, but this is a very good presentation because the main thing we want to remember is the general implicit function theorem. Great, thank you, Ryan.
Thank you.
Jazelia 4.113, the Ivy, Yuri, Israel, Josephine, Gregory 3.3, 11. I'm not quite sure what kind of question is that.
May I start, Miss?
Yeah.
So I'm doing 4.1 question 13, and the problem says the acceleration, comma, initial velocity and initial position of a particle traveling through space are given by a of t is equal to 2, comma, -6, comma, -4, comma, v of 0 is equal to -5, comma, 1, comma, 3, comma, r of 0 is equal to 6, comma, -2, comma, 1. The particle's trajectory intersects the yz plane exactly twice. Find these two intersection points. So the first thing I did was find the velocity vector, and this could be obtained by doing the integral of our acceleration. So I plugged in my values, so I get the integral of 2, comma, -6, comma, -4. When we integrate 2, we get 2t. Integrating -6, we get -6t. Integrating -4, we get -4t plus c. So see here, I just added the v of 0. So I get 2t, comma, -6t, comma, -4t plus -5, comma, 1, comma, 3. So 2t minus 5 becomes our ith position. -6t plus 1 becomes our j component. And -4t plus 3 becomes our k component. Then I had to integrate our velocity vector. So I plugged in the values over there, and I get the integral of 2t minus 5, comma, -6t plus 1, comma, -4t plus 3 dt. Integrating 2t, we get 2t squared over 2. Integrating -5, we get -5t, comma, integrating -6t, we get -6t squared over 2. Integrating 1, we just get t. Integrating -4t, we get -4t squared over 2. Integrating 3, we get 3t, and then plus c at the end. So I just simplified this first. So 2 over 2 gave me t squared minus 5t. -6 over 2 gave me, comma, -3t squared plus t. -4 divided by 2 gave me -2t squared plus 3t. And then for c, I just plugged in r of 0. So I get t squared minus 5t, comma, -3t squared plus t, comma, -2t squared plus 3t plus 6, comma, -2, comma, 1. And my final answer there was t squared minus 5t plus 6, comma, -3t plus t minus 2, comma, -2t squared plus 3t plus 1. And we know the particle's trajectory intersects the yz plane. So I had to take t squared minus 5t plus 6 is equal to 0. Factor that out to get t minus 3 times t minus 2. So the point of intersection would be at t is equal to 2 and t is equal to 3. So the last part was just to plug back into the equation. So first I've plugged in 2. I get t squared minus 5t plus 6, comma, -3t squared plus t minus 2, comma, -2t squared plus 3t plus 1. 2 times 2 gave me 4, -5 times 2 gave me -10, plus 6. -3 times 2 squared is -3 times 4, plus 2 minus 2 just gave me 0 there. -2 times 2 squared gave me -2 times 4. 3 times 2 gave me plus 6, and then plus 1. And so at 2, our point was 0, comma, -12, comma, -1. And then plugging in 3, I did the same thing. I got 3 squared minus 5 times 3 plus 6, which gave me 9 minus 15 plus 6. And then for the jth component, I got -3 times 3 squared plus 3 minus 2, which gave me -3 times 9 plus 1. And for our kth component, we get -2 times 3 squared plus 3 times 3 plus 1, which gave us negative 2 times 9 plus 9 plus 1, which in the end gives us at 3 a point of 0, comma, negative 26, comma, negative 8. So our intersection points was 0, comma, negative 12, comma, negative 1, and 0, comma, negative 26, comma, negative 8.
All right, thank you. Ivy, 4.19, then Yuri, 3.511.
So I chose to choose 4.1.9, and this asks, consider the helix given by CT equals to A cosine T, A sine T, and BT. Show that the acceleration vector is always parallel to the XY plane. So for the third component, it's a constant. So first, to find the acceleration, we have to find the velocity first.
Hold on 1 second. What do you mean the third component is constant?
It's BT, and I'm assuming that B is just like a constant number. So
The B is the scalar of a T. So BT, the T is still a variable. So BT is a linear. It's not a constant.
oh, okay. All right. So yeah, so it's a scalar. And first, we have to find the acceleration. We have to first find the velocity. Velocity is the derivative of the first vector, and that is negative a sine t, a cosine t, and b. After that, to find acceleration, we have to find the second derivative of the original, or the derivative of the vector, which is going to be negative a cosine t, negative sine t, and 0. And we notice that the third component is 0, meaning that there's going to be no z-plane. And
I think you're missing something. I think your calculation is wrong. Your second derivative. Look at your first derivative. You're missing something. Second component. Look at your second component.
oh, I'm missing an a.
Right.
If I added in. Yeah, I'm using a mouse, so it's really sloppy. And after that, we notice that the z-plane is 0. So there's so that kind of shows that the vector itself is going to be on the xy plane, which also shows as parallel to the xy plane itself, which proves what the question is asking.
Okay, hold on a second. So what's your conclusion?
That it's
The
always
second,
going to the acceleration
so
vector is always parallel.
Okay, why?
Because there's no z-plane, so then the acceleration itself is always going to stay on the xy plane. It's going to be like a flat surface.
Oh, I see. Right. Because the z value is 0.
Yeah.
Can the first two components be 0 at the same time?
No.
Why not?
Because I'm assuming that if you plug in 0 for each of them, cosine t is going to get you 1 and the sine t is going to give you 0.
Right.
So
Well, you could just answer cosine and sine will never be 0 at the same time.
yeah.
Okay. All right, fine. Thank you.
Thank you.
Okay, Yuri next, 3.511. Then Israel, 4.23. Yuri, I cannot hear you. Yeah, we're waiting for you. Okay, Israel, maybe you can go before Yuri. That's okay, Yuri.
Okay.
Oh.
No, it's me easier. Okay, so for 4.2.3, it asks us to find the arc length, and basically the arc length is defined as the integral of t0 to t1 of the magnitude of the derivative of c of t. Basically, and so our c of t for this question would be sine 3t, cosine 3t, and 2t to the 3 halves, between 0 and, where t is between 0 and 1. So we take the derivative, so we can then, plug it into the equation, which gives us 3 cosine 3t, negative 3 sine 3t, and 3t half to the power to 1 half. Then we just plug it into the equation above for arc length. Sorry, I had to. Apologies. And then we basically just take the magnitude of the derivative. It simplifies down to the radical 9 plus 9t, which we then take the integral of, which gives us, I did it in terms of u, just to simplify it for my sake. And it basically gives us 2 to the 20 over 27 times u to the 3 halves, which then becomes 2 radical 2 minus 2.
Okay.
That's just the gist of it.
Yeah, that's to calculate the arc length. Thank you. Yuri, are you ready?
Yes, can you hear me now, Professor?
Yes.
Oh, great. So, problem 3.5.11 asks to consider the function f of xy, which is equal x squared minus y squared over x squared plus y squared, comma xy over x squared plus y squared. And the question is, does this map of to space at 0, 0 to space have a local inverse near the point 0.1? So the first thing I do is just split up the function as kind of two functions, f1 and f2, and the first function, like subfunction, becomes the first component of function f. This is my f1, and the second function is the second component of function f. And now, after this, this problem becomes very similar to that one that Ryan presented earlier, the first one. It is sufficient to show that delta at this point 0.1 is not equal to 0, and then it proves that this function has local inverse at that given point. So by delta, we mean the discriminant of the matrix of partial derivatives of the functions f1 and f2. This is just the formula for delta, and I need to show that the discriminant at this point, x0, y0, is not equal to 0. So the first thing I do is just find the partial derivatives separately, because it's kind of a little bit long process. So I use, because we have a quotient, I use the quotient rule to find the derivatives, and the results of them are presented on the slide. I'm not going over it. It's just basic math. And then what I do next, I need to evaluate delta at the point 0.1. So I simply plug in 0 for x's and 1 for y's to find the numeric value of delta. And at the end, I get the matrix 0, 0, 1, 0. and the determinant of this matrix is equal to 0. And because it's not non-zero, I make a conclusion that the local inverse at that given point, 0.1, does not exist. And that's it.
All right. All right. Nice. Okay, thank you.
Thank you.
Josephine, 4.15, and Gregory, 3.311.
Can you just switch me to be a presenter, please?
Oh, I haven't. Sorry.
Okay. Thank you.
You're welcome.
Okay. So I'm going to present 4.1 question number 5. So it asks to find each of the stated derivatives in 2 different ways to verify the rules in the box preceding example 1 in this section. So that's the differentiation rules. So question 5 is really asking about the sum rule. So the first way that I found the derivative was, first I did, basically sum rule says the derivative of the sum is the sum of the derivatives. So first I added them and then took the derivative, and method 2 I took the derivative of each and then added them. So here, starting with, so adding them, the 2 vectors were e of t sine t, and then t cubed plus e to the negative t cosine t negative 2t cubed. So then adding them together, you get e to the t plus e to the negative t sine t plus cosine t, and then t cubed plus negative 2t cubed, and that's just really negative t cubed. So the derivative of e to the t is just e to the t. The derivative of e to the negative t is negative e, e to the negative t times negative 1. So instead of it being plus, it's a minus sign. And then the derivative of sine is cosine, and the derivative of cosine is negative sine. And then the derivative of negative t cubed is negative 3t squared. So then I get what's on the bottom as the derivative and in vector form. And then method 2, taking the derivative of c sub 1, I get the derivative of e to the t is just e to the t. The derivative of sine is cosine. And then the derivative of t cubed is 3t squared. And then I took the derivative of c sub 2, and I got negative e to the negative t plus negative sine t plus negative 6t squared. So then adding those together, you get the same answer as in method 1.
All right. All right. Gregory, last one. Gregory, if you're talking, I cannot hear you. And also, I don't see your screen sharing. Yeah, cannot hear you. Okay, let's wait for Gregory a little bit.
Okay. Good morning, Professor. Can you hear me?
Yes.
God bless. Okay, great. I'll share my screen now. Sorry,
Okay.
I got sick for the past few days, so I was a little bit behind. That's why I asked to present this question, but I really like it since the answer was different to all the other questions, right?
All
So
right.
I'll share my application. This one. Okay. So we can see this question, right?
Yes.
Okay, great. So 3.3, number 11, we're asking to find is there a critical point, local maximum, minimum, or saddle point, right? And so here's our function. F is equal to e to the x times cosine y. And the test that we have to do would be checking if the partial derivatives, all of them, equal to 0. So you do the partial derivative with respect to x, which would be here, which is e to the x times cosine y. And then with respect to y, which will be negative sine y times e to the x. And so our conditions for if it's a minimum or maximum would be if the partial is not equal to 0. If it were a minimum, the derivative of the surrounding points would have to be increasing, which would make the graph go up in the z direction, and the opposite would be true for the minimum. The graph would have to go down, and all the derivatives around it would have to be negative. And for saddle, we'd have to check if it's neither equal to 0 at the point 0, 0, and that will tell us the conditions for all of those, right? And so we check for the gradient of f, the original function here, e to the x cosine y, which would check for 0 is if it's equal to 0 in the following cases, where our gradient here defined by these partial derivatives equal to 0. And in each case, we find that it's not possible, since if we plug in 0 for x, y, or for both of them, we find that we never get the 0 vector. And for all cases, it's not possible, right? Thus, we can't have a critical point, we can't have an extreme point or local, and it's not a saddle. And we can go back to the text and find an example of a question with the same kind of dimensions. So we have a function R2 mapping to R1 with inputs x and y, and we have our function of R1, which is the same thing as we have here, and this would be the R1, and x and y just coefficients where x would be the e to the x. And in our solution, we find that we have no critical point, and there's no way of us getting to the 0 vector. And in our case, we have no relative extrema, and this would be an example of what the saddle would look like. And so here's our function. And if we zoom in at the axis, we can definitely see there is no saddle point. And I think this was the only type of situation for all the questions where there was no possible anything. And that's why I found it very interesting.
All right. Nice. Thank
Great.
you.
Thank you, Professor.
Thank you.
No problem.
Okay. Okay, so we have covered chapter 1, chapter 2, chapter 3. So we're going to chapter 4. But chapter 4, we're going to talk a little bit about, mainly is arc length, which is someone 4.1, 4.2. Yeah, some of you, yeah, Israel presented one question to calculate the arc length. So that's for 4.2. Vector fields, I'm not sure if I listed that homework. 4.4 is not our syllabus. Then next week, so after our exam, so chapter 4 will not be on our midterm. So next week, we're going to chapter 5, double and triple integrals. So the idea is very similar to partial derivatives. So we integrate in one component at one at a time. So same thing, so that you can understand like a partial integrals, which is integrate the function in one direction. at the moment. So we do one by one. And then after that, we talk about the change of variables. We're going to be using polar coordinates, cylindrical coordinates, and spherical coordinates to see why we even need those extra coordinates. Because when we integrate, sometimes the integrand is very difficult to integrate in Euclidean coordinates, x, y, z. But once we change to be other coordinates, the integration is much easier, super fast. So that's the purpose of change the variable. But when we change the variables, when we change the coordinates to integrate from two coordinates that have a relationship. So the relationship is differ by a scalar of Jacobi, which I think we touched on yesterday. The Jacobi, calculate the Jacobi, is a determinant of a square matrix. Then lastly, I think we touched on 7.1, 7.2. We talk about line integrals. Then we finish. All right, let's go to, so chapter 4, vector value functions. Now we see the path. We use a column vector to represent. All right, because the path goes from one space to n space. So capital letter DC is an n by 1 matrix, has n rows, 1 column. So we call column. So this is a matrix, n by 1 matrix, or a column vector. Sometimes for convenience, we write this way. Most of the time, for convenience, we write this way. But when we need to apply, when we are dealing with composition of functions, when we need to multiply matrices, so we want to represent it in the right way, all right? Right, and so someone has already, just a thing I think, already verified some of those properties. Sum rule. So differentiate sum of two paths is the same as the sum of the differentiation of two paths. Scalar product rule. Dot product rule. All right. Scalar multiplication rule. Because C of t is from one space, and P of t is just a function, just a single variable function. P of t is a single variable function. So this we call scalar multiplication rule. So we differentiate, but all of them, so this one product rule, this one product rule, cross product rule. So those three all involves product rule. So differentiation of the single variable function multiplied by the path, then derivative of the path multiplied by the function. For dot product, so it respects the structure, right? So this is a scalar multiplication. So the rule respects the scalar multiplication. For dot product rule, it follows the product rule, but respect the dot product. Okay, you see this is dot product, so it respects the dot product. Cross product, it follows the product rule, but with respect. So it keeps the structure of cross product. Right. Chain rule, dealing with composition of functions. All right. Let's see example 1. Show if C of t is a vector function such that the magnitude is a constant, then C prime of t is perpendicular to C of t for all t. So because the magnitude of C of t is constant, because C of t is not a vector, right? So this is the length of the vector, or the magnitude of the vector. If it's constant, so it's a square, right? It's just dot product of itself. Then we can use the dot product rule. Differentiate this, so we get twice of this, so we get twice of this. Well, if this is a 0, right? If this is a 0, remember dot product of two vectors, if it's 0, that means those two vectors are perpendicular to each other. So that's it. Right. If anyone has any questions, feel free to stop me. So far, so good. Anyone has any questions? All right. Okay, let's keep going, keep moving. 我在上课。
对啊。
Sorry, just
讲。
Sorry. So let's see example 2. A particle moves in such a way that its acceleration is constantly equal to negative k. If the position when t is 0, and that's is this position, and the velocity at the t equals 0, so C prime of t is this. When and where does the particle fall below the plane z equals 0? Describe the path traveled by the particle. Okay. So let C of t equals this, right? 3 components, because ijk. Because we're given this negative k direction, we have this ij. So we know C of t goes from 1 space to 3 space. Then C prime, of course, can be represented as x prime, y prime, z prime. The acceleration is negative k, so that means second derivative in x direction is 0, second derivative in y direction is 0, and second derivative in z direction is negative 1. And first derivative of x and y are constant functions, right? Because it's the second derivative is 0. And then z prime is linear because second derivative is negative 1. Because c prime of 0 is 1, 1, so we integrate, so we get this. We get 1, 1, negative tk. But then integrating again using the initial position 0.01, we can conclude C of t is t, comma t, 1 minus half t squared. But this is basically integration and plus initial points or initial vector. We can always do that. Anyone has any question? All right. I think Jazelia showed one question similar to this. Let's see example 3. A particle moves along a hypercolloid. Remember this one? According to the equation, we don't really have to remember this, all right? Just we have this equation, x equals cosine cube t, y equals sine cube t, and the t goes from A to B. What are the velocity and speed of the particle? Okay, what's velocity? Velocity can be positive, can be negative, right? But speed is magnitude. Velocity also is a vector, so speed cannot be negative. speed is the magnitude of the velocity vector. So velocity vector, we just take a derivative, right? So we get negative 3 sine t cosine square t in first component, 3 cosine t sine square t in second component. And it's a speed, we just calculate the velocity, magnitude of the velocity vector. So we just square the first component, square this component, plus square of the second component, then square root. So once we square root, we get a 3 sine t cosine t. Because sine is being squared, cosine is being squared, and under square root, so we have to force sine t cosine t to be non-negative, which will put an absolute value around it. So put an absolute value around it. That's all I want to talk about in 4.1, right? It's good enough we know how to calculate arc length. So what is the speed? So in this case, all right, just one thing. So velocity is a vector, can be 0, can be positive, can be negative. Right? Speed cannot be negative. So speed is the magnitude of the velocity vector. So that's 4.1. 4.2 arc length. And Israel already showed us how to calculate the arc length. It's this, remember, single variable calculus, right? On the interval from t0 to t1 and c prime of t, so the speed of c, the magnitude of the velocity vector is the integrand. Then evaluate from the lower bound to the upper bound. For us, we're dealing with the vectors, so c goes from 1 space to 3 space, and t goes from t0 to t1. So L of c, the length of this arc length, or this path, is from the lower end of t0 to the upper end of the integral t1. And the square root, which is magnitude of c prime of t. What is magnitude of c prime of t? It's x prime square plus y prime square. So if you draw a picture of it, that's applying Pythagorean theorem once, then plus z prime of t. So apply Pythagorean theorem again. Let's see an example. The arc length of path c of t, r cosine t, r sine t, right? What is this? The penetration of the circle centered at the origin with the radius of r. For t lying in the interval from 0 to 2 pi, so t0 is 0 in this case, t1 is 2 pi in this case. X of t is r cosine t, y of t is r sine of t. So first we just have to take a derivative of c prime of t, right? That would be negative r sine t and r cosine t. Then we square both. We square root. That's going to be the integrand. Lower limit 0, upper limit 2 pi. Then we integrate this. Once we integrate, we see the first one give us r squared sine squared. Second one give us r squared cosine squared. Factor out r squared. So we have sine squared plus cosine squared, which equals to 1. Or square root of r squared, just r. Okay. So we calculate this. In the end, we get a 2 pi r, which is obvious, right? Because C prime of t from 0 to 2 pi is just one circle centered at the origin with radius r. So the length of the path is the circumference of this circle with radius r. Well, let's see this example. So position function is t minus sine t, 1 minus cosine t, which traces the cycloid. Remember, cycloid is we mark a point on the wheel, then when the wheel runs, right, the mark makes a trajectory we call cycloid. So we want to find the velocity, speed, and length of one arc. So C prime of t, we'll take derivative, 1 minus cos t sine t. Then we calculate its magnitude, square root of first component square plus second component square. It's going to 2 minus 2 cosine t. So that's the speed, right? So velocity vector, speed, then the arc length of one arc. So that goes from 0 to 2 pi. Integrand is magnitude of the velocity vector. And how do we calculate this? We rewrite this as half of 1 minus cos t, right? We want to use half angle. But we have to offset 4 because it was 2 before. Now we do half. So half times 4 gives us back 2. But 4 can be pulled up from the integration because square root 4 is 2. The square root of 1 minus cos t over 2 is a sine of t over 2, half angle formula. Because 1 minus cos t equals 2 sine squared t over 2, right? Remember that. Then sine of t over 2 greater than or equal to 0 on 0 to 2 pi. So we integrate this. So we know sine comes from negative cosine integration, right? And the t over 2, we have to offset when we integrate, right? When we integrate, we have to multiply by 2. So 2 times 2, that's 4. So sine of t over 2 is negative 2 cosine t over 2. So we evaluate from 0 to 2 pi. In the end, we'll get 8. So the arc length is 8. Any question? Example 3, the little difference is, you see the first component, x of t, is absolute value of t. The second component is t is absolute value of t minus half. The z component is 0 because it doesn't show up here. So the path is not smooth, right? It cannot be, so the path cannot be differentiated at the cusp. Because the absolute value function has this vertex. When we talk about differentiability, we call the vertex a cusp, cannot be differentiated. Because one way, because you have this absolute value function is like a V shape, right? So from the left-hand side, you have the left branch, the left line. From the right-hand side, you have the right-hand side line. So the two tangent lines are totally different. So that means when we differentiate, so we cannot differentiate because there's two possible values. So if we divide the interval -1 to 1 into -1 to 0, 0 to half, half to 1, then we can differentiate. So we ignore the vertex, we ignore the cusps. Right? We ignore the vertex or the cusps. Yeah, the picture is like this. Right? You see, we have this vertex, we have this one. So at these two places, at the 0, f, the path cannot be differentiated. So we have to separate into different intervals to ignore 0, ignore half. So on 0 to 1, we get negative t plus half. So the arc length of C between -1 and 0 we set up, right? We have this because the arc length, the magnitude of vector in from -1 to 0 is square root 2. So just integration from -1 to 0 square root 2, and which equals to square root 2. Right? So similarly, we do 0 to half, and again we get square root 2. And on half to 1, we can write this way: the arc length between the arc length of C between half and 1 is half of square root 2. A little bit different from, so it's a half of the previous 2. So the total arc length is just adding them together. So we get 2 radical 2. Okay. So we can just ignore some points, right? Let's see example 4. Find arc length of cosine t, sine t, t squared, and t goes from 0 to pi. Well, we need to find the velocity vector, which is the negative sine cosine 2t. Then we find its magnitude. Right, we get a function of t. Then we put in the arc length formula. Then we try to integrate. In the end, we calculate. So in the end, it's about 10.63. We don't care about the units. Okay, this is pure mathematics. We don't care about the units. Anyone has any questions? The differential of arc length. Okay, so differential is a term, right? It's not a derivative, it's not differentiation, right? It's called a differential. So the infinitesimal displacement of a particle following a path c of t with 3 components is a ds. ds. So infinite displacement equals to dx in first direction, dy second direction, dz in the third component. Or we can write this way. Because we're treating the first component x as a function of t, second component function of t, third component function of t. So we can write as dx dt, dy dt, dz dt, then offset with the dt outside. And its length ds equals square root of dx squared plus dy squared plus dz squared, or dx over dt squared plus dy over dt squared plus dz over dt squared. Then differentiate in t. So this is called a differential of arc length, right? Differential arc length. Yeah. Then we see we can just write the arc length L of C as this. Right? Lower limit, upper limit. Then the integrand is ds. So the integrand has this, has the arc length and dt. This thing, the arc length formula can be extended to nth dimension. Let's see this one. Find the arc length of this 1, 2, 3, 4 dimension, 4 space, right? From 0 to pi. Well, 4 space, the arc length, we just have to apply Pythagorean theorem 3 times. In the end, we get square root of 5. So plug in the arc length formula. From 0 to pi, square root of 5. In the end, we just get square root of 5 pi. Okay, so we're going to cover, so chapter 4, vector fields, I think it's an optional one too. Vector fields is a very important concept for physics. What can be for other science majors? So let's see. A vector field in Rn is a map, right? It's going from n space to n space. So assign one vector, if you look at this picture, 4.31, assigns one vector to be another vector in the same space. If n equals 2, F is called a vector field in the plane. And if n equals 3, if it's a 3-dimension, 3 space, it's a vector field in space. So this picture 4.31 shows us a vector field. Right? So you see we have a couple of vectors and they created a field. Right, gradient vector creates a gradient vector field. Right. Example saying, show this is not a gradient vector field. Right, take the gradient, we get a y comma negative x. Because there are first level derivatives exist, so f itself must have a common first and second order partial derivatives. So which means the mixed partials have to equal to each other. But if we calculate partial square f partial x partial y, we get -1. If we calculate the partial square f partial y partial x, we get 1. So -1 and 1 not equal to each other. So this vector, so that's why it cannot be a gradient vector field in Euclidean geometry. A cute example, counter example. Okay, that's it. That's all I want to talk about in chapter 4. A simple chapter. Okay, so next week we're going to chapter 5. And If you're interested, if you have time, you know what, probably you don't have time because next Monday, which is my Tuesday morning, your Monday evening, we're going to have our midterm. All right. Right. It's a lot of practice. So next topic is double, triple integrals. All right, anyone has any questions? If you have no questions, you are free bird. You can go ahead, do homework for chapter 4 or study for exam on Monday. If you do have questions, I'm still here to answer your questions. All right, that's it for today. Thank you, Ron. Thank you. Thank you, Israel. Have a good evening. Good luck on Monday. Thank you. Oh, you too. Have a good weekend. Thank you. You too, Gabrielle. Thank you. Liz, it's too late. I already finished the class. Yeah, you can present next time, one at a time, not two, one at a time, okay? We still have time.